Hello everyone. Thank you for your kind interest in the Computational Molecular and Materials Modeling course. I am Vivek Sinha. I belong to the 2009 batch of IISER Kolkata. I graduated in 2014 with a major in physics. Now, for this introductory video, I was in two minds about whether or not I should build a slide deck with, snapshots from my papers and stuff or not. But then I thought that let's use this video to personally connect with all of you. You can, of course, look up my work, my papers, and I'll share some links. But today I want to connect with all of you and share my story and motivation for this course, and then set some expectations for this course. So, like many of you, I wanted to be a researcher, a scientist. I joined IISER Kolkata to become a scientist. And I remember back in the days, the selection was through IIT, and I was having my counseling in 2009 in IIT Guwahati. And the counselor said, hey, you want to become a scientist? Why don't you join IISER's, IISER Kolkata or Pune? So I did that, and that was a great moment. I came to IISER thinking I would become a scientist now. And then my seniors, they said, you know what, go to IISER Chemistry. You'll work at Bioatomic Research Center and you'll have a great life and blah, blah, blah. And I went there. So it's when in December of 2009 at the NIUS Chemistry Orientation Camp in Mumbai, I came across computational chemistry. And I was instantly like, wow, this is what I wanted to do. I mean, at school, I used to think, why can't we use laws of physics, like, equations of kinetic energy and the school of interaction and everything to study chemistry. But my teacher said, I don't mix physics and chemistry. I didn't mix them, but when I learned about computational chemistry, I was like, wow, you can model chemicals, you can control how chemicals behave, you can build molecules in computers, and that sounded very cool. So I worked at this Bioatomic Research Center as a summer intern for 3 summers, as an US fellow, later as an IAS fellow. I worked on molecular dynamics simulations to understand protein-drug interactions. I also worked on quantum chemical simulations, density functional theory to understand host-guest complexation and binding of certain cations in certain macromolecular complexes. Actually, I was quite into it, really driven by it. So I ended up publishing 4 research papers during my BSMS at IISER Kolkata. And later I went for a PhD at University of Amsterdam. This was under a very peculiar Shell PhD program. It was a 5-year program. They ran for, to hire people in India, offer them a job, but then say, hey, you could also pursue a PhD in the Netherlands and then come back to join Shell Bangalore. I didn't end up joining Shell Bangalore. Life happened, but so I got into this program. I worked very closely with Shell. In my project, I did a lot of modeling of catalysts, mainly for clean tech applications, for hydrogen production storage applications. Most of the work was on homogeneous catalysts. I also did a lot of wave function-based calculations, CAS-SCF-like calculations to understand the electronic structure. And most importantly, I learned about this ab initio molecular modeling to treat explicit solvation effects in catalysts, something that I'll also talk later in my course. This was very useful. And after that, I did a couple of postdocs at TU Eindhoven and TU Delft, where I worked on modeling catalytic surfaces. So no more homogeneous catalysis. I still did some homogeneous catalysis, but the focus was mainly on catalytic surfaces. I did multi-scale modeling simulations of electrochemical transformations like CO2 reduction reaction on silver surfaces or water oxidation on hematite. I also performed some data-driven chemistry research. I'll also touch upon that a little bit in my course. And then I worked at a clean tech startup, also modeling materials and designing catalysts. And then I made a career move. I went into quantum computing as a technical manager. So I now work at TU Delft at a research institute called QTech. And I'm in charge. I'm the project lead for scaling up quantum computing hardware, especially for the superconducting backend. I think I'll also have a guest lecture in the quantum error correction course, so you can learn more about that there. But I am still very much at heart a computational chemist, a material scientist, and also quantum computing applications connect very well with that. But we can talk about that later on. So it has been an interesting journey for me. But that's enough about me. Let's just talk about course, and I'll also motivate why I wanted to offer this course. First rule of the class, there are many of these fantastic lectures out there on YouTube, on different forums that talk about theoretical integrities and fundamentals and getting things really accurate and right, which is very important. But that's not the focus of this course. I mean, we are not going to do wrong stuff, saying that we can do any level of theory or anything. That's not what the point I'm trying to make. The point I'm trying to make is, I have been working in this field for like over a decade now. I've also interviewed many, postdoctoral candidates or candidates for computational chemistry roles. And what I really identify is that there is kind of a gap where no one talks about really practical stuff that matters most when you are working in the field. There's a lot of debate most of the time in density functional theory, and people come up with all kinds of the sophisticated tests, and there's no consensus. There is no sort of rule of thumb that you can get started with, and that you can continue to work on and improve upon. I mean, the first time I started using Gaussian, that was back in 2009, 2010. I remember a postdoc in that lab started like sort of quiz me, saying, "Hey, do you know this? Do you know that? Oh, you don't know what these terms mean? How do you even use it?" And I was a bit confused. I was like, "Okay, that's a lot to learn." I mean, I could start reading up, textbooks and get lost into all the quantum chemical jargon, or I can also start doing things, executing things side by side, and that worked out very well for me. I got advice from the professor that I was working on, like, it's important to learn theory, but it's also important to learn by doing. So that kind of helped, and that's something that I want to emphasize upon, that we learn by doing. I'll try to give you introduction to everything that you need to know about the basis of computational chemistry, things like, what's the Hartree-Fock method, what's density functional theory, wave function-based calculations, exchange correlation functions, basis sets, how to deal with explicit solvent, what's geometry optimization, how do we even calculate thermochemical properties and everything. But I want to do this with minimal equations, not because I hate equations or because they're not important, but because they're not really necessary for you to get started or to derive science or derive insight out of these concepts for the first time. I mean, of course, theoretical rigor is very, very important. We're dealing with exact sciences here, but I will make an honest effort to make sure that it's useful for everyone at all levels. And then we'll look into some basics of how to create molecular geometry, set up basic calculations, how to use chemical databases, and a very useful tool called atomistic simulations environment. And with regards to tools, I will use open source or free versions, like GFN2XTB from Grimm's group, Orca, atomistic simulation environment, GPaw, etc. I will, however, give you a framework that you can apply to other suite of software as well. So especially with ACE and the use of databases, you will be able to do file conversions. You will be able to generate input for other software suite as well. I mean, look, I think I have used almost all of the popular computational chemistry software in my career so far, and it's not the tool that matters the most. I mean, it might seem like, and the first time I started using Gaussian, I was like, oh my God, what do these terms mean? How do I get started with this and that? But it's important not to get lost with the nitty-gritties of a software. It's important to understand how to have like sort of a general purpose framework to work on. And of course, if you have specific software related questions that I can help with, I will be happy to help you there. The format of the course will be highly hands-on. So we will mostly work with Google Colab and Jupyter notebooks. And don't worry if you are not good with programming or if you're not familiar with programming. My job is to remove barriers. So I won't let Python programming be a barrier in your learning. I can assure you of that. And so I will also touch upon, how to set up surfaces for heterogeneous catalysis in general, perform some basic calculations. Mostly, I'll focus on calculations that can be done within the time frame of the course. So no HPC simulations with multi-course or something, because that's not within the scope of this course. You can use that for your capstone. And yeah, finally, I will touch upon a use case of modeling reaction mechanisms in homogeneous catalysis. But my focus is not just to tell you about how to do things in homogeneous catalysis. I will talk about certain applied scenarios. I'll also tell you an interesting story about how we worked with different groups, and we had quite a bit of conflicting ideas with a very famous catalysis group in Germany, and how we amicably resolved it. We visited them. We came up with certain new mechanisms for hydrogen evolution reactions. So a little bit of, not a lot of story, but a little bit of background there. I'll also tell you how I dealt with explicit solvation and why it's very, very important in modeling reaction mechanisms, and how to do it at a moderate computational cost. That's also important, and how to benchmark certain methods for for particular use cases, all based on my research. And finally, I'll tell you about the capstone project and organize an open Q&A session. I won't be able to touch on certain very niche topics like modeling polymers or large scale MD simulations. I'll be happy to touch upon them during the open Q&A. At the end of this course, you will be equipped with a portfolio of work that you can share with, for your applications. It will also be of practical use in your own workflows if you do production grade simulations. And everyone who has completed the capstone will get a participation certificate, so there are no pass or fails here. I also aim to use this opportunity to build, even in the near future, a community of motivated computational chemists, material scientists, and there will be more editions of this course. I also plan to do something on building careers in computational chemistry and beyond. What are other areas that you can work on? Like you can become a technical project manager like I am now, but much more. And yeah, for some of you, I will be happy to write recommendation letters based on how we interact and your performance. So yeah, that was all. I really look forward to welcoming many of you there at the course, and please feel free to reach out to me if you have any specific questions or just general question. If you want to drop and say hi, feel free to connect me on LinkedIn. Yeah, so that's about me, and I look forward to seeing all of you there. Bye bye.